Today I'm gonna show you very quickly the schematics that I've prepared in Fusion 360 or Eagle that I will use to produce the PCB for the master fader that I have shown you in the last video. As usual, guys, I kindly ask you to subscribe to the channel if you are new or if you haven't done yet. And to give a thumbs up to the video if you like it. This is very important for me. What you are seeing is the full schematics for the master fader that I just completed. First of all, I grouped everything in one single sheet for two very good reasons. First one is because it's gonna be easier to show up into the video, and the second is because the version of Fusion 360 that I have doesn't allow me to have more than two sheets. So, I mean, at the end of the day, it was a kind of no-brain decision. Here you have the STM32F072, which is the microcontroller that I used for the master fader. As you can see, in terms of package, it's easy to see that it's a little bit an overkill because there are a lot of lines which are not used. But this is the one that I had available, so I mean that was again another no-brain decision. Let's analyze first of all the way it is structured, the circuits around the microcontroller. As you can see, and following the data sheet, what I have prepared is a series of decoupling capacitors in the main power in, which are substantially two, the VDD and VSS 1 here, and the VDD VSS 2. As I said in the datasheet, it was specified that there was the need of a strong decoupling. Probably this microcontroller is quite sensible. It's a series of decoupling capacitor for 0.1 microfarad, 3 of them, and then the last one 4.8 microfarad, and the same here on the other power input. Then we have here we have the VDD-IO and the VSS. It's another power input. On this, the datasheet was specifying to put two decoupling capacitor, one for 0.1 microfarad again, and the other one, let me check, is for 4.7 microfarads. Okay, fair enough. Then we have another series of decoupling capacitor here. This is the VSS-A and the VDD-A. This is for the analog, for the ADC input. And again, two decoupling capacitor, one for 0.1 microfarads and one for 1 microfarads. There you go. On top of this, we have the lines for the LEDs. As usual, I put several LEDs on the circuit because this helps me a lot in debugging the application. First of all, we have the power green LED here with its own resistance, and then what I call the heartbeat LED with its own resistor. The heartbeat is nothing more than an LED that I switch on every second, connected to a timer to verify that the boot up of the microcontroller worked correctly. Then we have here other three LEDs. We have the RX and TX LEDs here with its own resistor for the UART, and we have here the LED, the orange LED for the what I call the operation LED. Operation is the LED that is blinking when the fader is moving autonomously upon feedback. And finally, we have the last one here, which is a red LED for touch, and I switch on this each and every time I touch the fader. Every LED, of course, has a resistor. The value of the resistor is something that I have calculated. Actually, when I do this kind of circuits, I tend to choose LEDs which are not too bright, because as I said, I use these lights for debugging purpose. I don't like to have very strong lights in front of me when I work, so typically I put resistors which are over the value that is recommended or is that you can calculate based upon recommended specification from the LED. And in fact here, for instance, on the green LED I put a 5.6 kilo ohm resistor. These LED normally are very bright. With this resistor it's visible, but it's not too annoying for my eyes. Same as above, for instance, here for the orange one I have 1.2 kilo ohm resistor and a 680 ohm resistor for the red one. Then moving on the ADC, you see here we have the PA0, PA1, which are the two lines for the ADC conversion. Two lines because the Born's motorized fader have two tapes and two lines. I typically connect both of them and then I use the one that looks to me more precise and more stable. Then we have here the circuits for the capacitive touch according to the TSC peripheral from STM32. In order to connect and integrate the capacitive touch, you have to dedicate two lines. One is for sampling, and you connect it with a small capacitor, 0.1 microfarads. This is used by the TSC as a reference for the acquisition of the touch, and one here which is the touch itself, the line connected to the motorized fader. Here the specification from ST says to use a resistor for 1 kilo ohm. Of course, this is just a suggestion. You will then use on the basis of your experience what for you works better. For me, using 1 kilo ohm resistor was a good choice. It works very well. And then there is a capacitor here, very small, this 22 picofarad. The specification from ST say that this is the most important capacitor. It should be small because it's on this capacitor variation of the capacitance that the TSC peripheral can really understand when you touch your sensor. You have to consider that when you touch your sensor, the variation into the capacitance of the circuit that you generate with your body is very small, in the say matter of 5-10 picofarads. So this is the reason why you have to use a very small one, because as soon as the change into the capacitance happen, it must be immediately visible to the TSC peripheral. Here we have the two lines for the UART, so TX and RX. Then moving on, here we have the two lines for the SWD, so to program the microcontroller. So we have here SW clock, this is the clock, and the SWDIO, this is the input output, so the line for data exchange. And finally here we have the reset, which is needed to reset the circuits. We will see it in a moment, and is also needed for the SWD interface. That's it for the microcontroller itself. We move now to the power supply, which is this. As I have explained, the main voltage of the circuit is 9 volts in order to power up the DC motor that moves the motorized fader, and for this reason I need to use a voltage regulator in order to bring the 9 volts to 3.3 and power up the microcontroller. What I use is Max 604 ESA. It's a voltage regulator that is already set to bring every voltage, I think until 11 volts to 3.3, so it's already set. You don't need to make any, let's say, other setup in order to obtain the voltage that you need. I set here another series of decoupling capacitor. Again, this is not really needed or requested from the datasheet, but during the prototypation, the experimentation, I noticed that adding this series of decoupling was bringing much more stability into the entire master fader circuit. Again, this is saying to me that this microcontroller is very sensible to noise and to disturbance on the line. Of course, also the voltage regulator have two decoupling capacitor here for 10 microfarads. And then you have here the input at 9 volts. So this is the input 9 volts, this is the output at 3.3 volts, and then the ground. Then moving on, here you have the BD6221, which is the motor control IC, single channel IC. First of all, you have the inputs at 9 volts here and here. Actually, these are two inputs at 9 volts, and this is the voltage reference, but it's again connected in the same line for 9 volts. You have then the two outputs here and here that goes to the connector that will be connected to the DC motor. So this is the output for the regulated 9 volt. And most importantly, you have the forward in and the reverse in here, which are connected here, here and here to the microcontroller. These are the two lines connected to the PWM. We have here a momentary button in order to reset. This is very easily connected to the reset line here and here, and is connected to ground via a pull down resistor of 10 kilo. Finally, we have here the three headers that are used to connect the circuits to the main custom board. You have the power here at 9 volts. You have the TX and RX USART connection that will be connected to the USART into the main board. And you have here the SWD IO, the SW clock, and the reset for the SDO for the SWD interface to program the microcontroller. Here you have the connectors that are soldered into the motorized fader. You have the two lines output for the linear potentiometer here and here, which are obviously connected here and here to the microcontroller. We have the two ground for the two tapes, and you have the two positive here and here for the two tapes again. And finally, you have the circuit of the touch. That's it. Next step, I will be producing the PCB, which I will also show as soon as this will be done. Thank you very much.